Actually, I will follow the instruction one by one. The second step is to create a new virtual environment. So I will type conda create n. Maybe I will use this one, Cadria, without the 2020, and I will type Python equal to the 3.5, this one. And you can see it's establishing a new virtual environment. And I will tap yes. Okay, then the next step is I will activate this virtual environment. So I will type this one, activate Cadria. Yeah, you can see the environment name is changed. So this is the most important step. That is, I will install all the necessary packages. So actually, for my part, I think the only problem is because of the network condition. So you have to try it for several times to install them successfully. Because I will try to install the first one. I will type conda install create manhole open this one. I think I have already downloaded it again successfully. So I have already have the pic of it. So it will be very fast. I can type Y. So it's already installing this kind of things. But actually, for most of the people, because they are it is their first time to install this kind of things, they have to wait for several minutes, for maybe 1 hour to install all the things. Actually, the first time I install this packages, it takes me nearly a whole hours to wait for the downloading. So it is really common if you met any error.
By the way, just adding something. Guanqi is in mainland China, so his internet condition is probably more complicated than most of you. Yeah.
Yeah. So because I have already downloaded all the things, it will successfully to install all the things. So I think maybe if you have any problems, you can share your screen. So actually for my computer, it's already it's already installed. Yeah, that will be no problem during my installation.
So my issue is when you install the third package, MV Conda, it says, it says because the environment was using Python 3.5, it failed to install that particular package. I wonder what will be the way to work around.
So actually, I remembered you are using the 3.8 Python.
Well, I wonder that if I change it to 3.8 directly in my environment, will that impact the code that we are using in Jupyter?
When you change it to 3.8, there will be error when you're trying to install Keras. So you're currently on 3.5, right?
That is correct, but I'm not able to install the third package because it's telling me that the MB conda is only for 3.8 or higher.
Oh, did you manage to install from the navigator?
I was hoping that you guys can show that particular process because I wasn't able to find a way to install it in the navigator.
Okay.
I'm having the same issue, exactly the same issue as you.
Okay, I think the thing is that I'm having it in my navigator because I installed it separately. So if you go to just Google Jupyter Network, Jupyter Notebook in Google. So.
Dan, can you share your screen?
Yes. I'm not entirely sure if it's gonna work, but it's like one option because mine is already installed on Jupyter Notebook and installed on Anaconda. And so if you go, you just Google Jupyter Notebook and over here. So can you see it?
Yeah.
Yes, thank you.
Just go in there. There's like a big sign called install. And getting started with your Jupyter Notebook, and there's something here, Conda. Try this line of code and see if this will work.
Should we install it directly in the Anaconda prompt?
Yeah, just type this one in Anaconda prompt and see if this line of code works.
Yeah.
Dan, one quick question. On me, it's happening the same on the Anaconda prompt. It's saying the same as I have Python 3.5, but on my Anaconda Navigator, Jupyter does show as launch. Like I could run it. I don't know if it's fine.
I think it would be great. Is it in this environment? Or is it in base?
It's on base.
Then you in here, you change it to casual, like, or whatever your name is. My name is casual 2020. Yours could be just casual. Just change it to the environment you are using and just click on install from here.
Oh, okay. Yeah. That was it.
Yeah.
So I just install it on the environment on Casual 2020, and I go back to the prompt to install the remaining environment. Sorry, the remaining installations. Libraries. Yeah, sorry.
Yeah, the remaining library.
Okay.
Hi, Dan.
Thank you.
Yes.
If we manage to install Jupyter Notebook on Anaconda Navigator, we don't need to run the NB Conda and prompt, right?
No, those are exactly the same thing.
All right, sure. Thank you.
Yeah, just sometimes people are more comfortable with the graphic interface. Oh, and for the other question, like I forgot who was asking, like you cannot get into this directory. Here. I vaguely remember there was a question about getting into this directory.
Yeah, I actually have this problem.
So ideally, you have downloaded the repository from Git, right?
Yeah, I did.
So open your your folder. So ideally, if you open your folder in the normal Explorer, like it should look like this. And copy this one. Copy this one. So because mine is already running, so I'll get this a new one and a kind of prompt. So activate. So first of all, you're in this environment, and your Anaconda prompt looks something like this, right?
Yes, true.
And you type CD and the space, and your paste like whatever you have copied here. And just let it go. Yeah. And then next line should looks like this. And here you open Jupyter Notebook. And that should get into the directory. Can I have a raise of hands for whoever is already in that directory with no problem of libraries and things? You can raise a hand in Zoom. Yeah. Like in the reaction, like here. Yeah. Perfect. Good. Yep. Awesome.
Can you hear me?
Yes, yes.
Where did you copy the directory from?
From the, you mean the directory? Did you download it?
The path, the file path.
Sorry, what was the question?
The file path, you have copied a file path, right? Which one should be copied for the file path?
So in here, so those three. So are you in here already?
File path you copied, right?
Yeah, it's the part I copied is just here, just the directory here.
Can you share your screen?
Sorry, here. So I basically just copied here. So this is where I have downloaded everything from GitHub. And if you open that GitHub folder, it should look like this. Everything you have cloned from GitHub. And when you're in this exact folder, you could just copy whatever the directory it is, like from here.
Okay.
Yeah.
Fine, thank you.
Yeah, no worry. And you just use so someone is missing the CV2. I think CV2 has a special download channel. Guanqi, can you share the conda install line for the CV2 in the group chat?
Okay, this one.
Yeah.
Actually, if you use pip install CV2, I think that will not work. You have to use this install OpenCV. This one, yeah.
I ran in the Jupyter notebook. I was able to run the library as you were previously instructed. And in the model one, when I ran the library, and it says, okay, using TensorFlow backend. So that is the normal reaction.
That's a normal reaction, means you have TensorFlow installed. Yeah.
Thank you.
Yeah.
I have tapped the CD and the folder, but it's nothing happened. I don't know why.
Can you share your screen to see what you have typed?
Yes.
Yeah. Huh, that's weird.
Oh, that's weird.
Can you put it in somewhere in disk C?
Okay. Just copy this folder.
Yep.
Can I put it here?
Yep.
I know that. Oh, sorry. If you have it in the D folder or E folder, after CD, you will have to do a slash D or slash E.
Right. Like one more slash.
Yeah, and then copy the link. So yeah, CD and then / or space and / E.
This one?
No. Yeah, that one. And then E.
Yeah.
And then copy your link. You have to type another E.
Additional E to change the drive.
Copy this one.
Yeah, copy that link, and then type another. Oh, one before more that, yeah, one more E.
Yeah.
Yeah. E.
Yeah, capital E, I think. Yeah.
Like this.
One more space.
Oh, okay.
Right. How to change the drive?
I lowercase e. I use lowercase e. It works for me.
Excuse me, can you repeat your first line of your Anaconda promote? The first line, yeah. The CD. And then input the direction of your folder.
Direction.
Yeah. And press enter. And you can type can type E.
E.
And one. This one. Yeah, you can see it's already changed. So you can try to open the Jupyter.
Okay.
Yeah.
Okay, thank you. I will have a try.
Yeah. Well, actually, I think the code is same. Yeah.
Yep. Yes. So I think it's okay to use other operating systems. It's just that where I'm using Windows, Guanqi is using Mac. If you're not using these two operating systems, we may not be able to help you debug certain bugs that are system related. Okay, so there are 3 parts. I think I'll go through them like early tomorrow morning, and there are one thing like the model part. I'll go through right now because this one relates to the neural network work model, and I'm hoping if we can, maybe I'll give everyone like a preview of things. So if we're able to squeeze in some more contents, we may be able to work on our second example on the third day, or otherwise we can only have time for the first example. So our second example will be more image based. That is like predicting the performance of the timber, which is like MOE value, module of elasticity value. If you don't know this one, basically it means the timber strength based on the timber grain. So this is like a image-based exercise. And if we have we're able to squeeze in more content, we may have time to work with this one. If we don't have time to play with the code, but I'll just go over it and go through the main concepts. The system is very straightforward, and you should be able with a little bit of research to work with it yourself. But let's hope we can have more time to squeeze more thing into the content, so we can have some time to play with the code on the second day or third day. Is someone talking? Yeah. Oh, sorry, I'm not sharing my screen again. Thank you for reminding me. Yep. So I'll give everyone like a preview of things. So this is like prediction of the module of elasticity value, which is like the strength of the timber based on the timber grains. It's like small exercise, but it's nice because it deals with two-dimensional information, because currently we're only doing working with one-dimensional data sets. So if we have time, we can play a little bit with this model as well. So so if everyone is having their thing like properly installed, and hopefully everyone can see my screen, and open this file called the model. I think there's a paper that describes the process on it. So I have included the link in there. It's like a Cadria paper like 2 years ago. And in case, ideally, if you have like shift enter the first line and everything runs smoothly without any warning, means you have everything here that you need. And just, sorry. No, sometimes you need to run it again. Okay, so if something shows up like this, like name NP is not defined, means you didn't import the library. But ideally, if it works, if you shift enter each line, this number should pop up. So this is like I have just given like already formatted data sets, and there are like in the other ones, the movie to image, and this is blocking the view. And in the image processing, it has detailed scripts on how to on how to format those data that we can go over like tomorrow morning. But I think let's just focus on the neural network model first. Now, this is like a data set I have already cleaned. So there are 1,456 pieces of information. So those are basically 1,456 strips. That's like full-length strips. And in this way, so those are like prepare the data sets. So when we unzip these data sets, we get the mid curve, bottom curve, vector at each interval, and the thickness value at each point. So remember, like mid curve, bottom curve, vector, which is like the gradient and slope at each feature point, and the thickness of the material at each feature point. And here are a bunch of like data formatting issues that just don't bother about it. It's just the way we're formatting the data that you have to match them one by one. And the reason we're doing this reverse cardinality is that just look at this one. This one is the data structure and the value that we're using for training. And if we are looking at one of the previous one from the models, from the image processing here. Yeah. So notice, because in image processing, we're using the OpenCV. Did you see where the 0 coordinates is? So there are a lot of like nuance. The system seems so easy, but like in the process, there are a lot of nuance. So you see, like in here, the X start here and the Y start here. But normally in real world or in architecture world, we want them like 0 to both start at the like lower left corner. So this part is about just to flip the coordinates of the vector, of the position, and etc. So if you're able to just go along each one and get something here, means everything is working so far. And then we look at the length of the thickness. There's like 1,456 piece in there. A little practicality about machine learning. So almost in all data sets that are massively generated, there will be some anomalies. For example, maybe because of like a lighting issue, maybe because some image, like you have a glare at the corner that you cannot read like one curve very correctly. Some will read like very thick, some will read very slow. So normally we would create a graph of the distribution. So this is a distribution of all the thickness. So you'll see like most of the thickness would fall into this region. Between the like 6 of, because it's all normalized, so it's not corresponding to the real thickness. But basically, if you're just looking at the value, you say most of them are between like 0.3 and 0.6, and there are some like some rubber pieces that are just too thin or too thick. Normally, we would get rid of them because though some may be real like samples, some were like they're more likely just anomalies problems. So normally we would start to look at the distribution and get rid of all those like standout values at the both end. So this is the same. So this one is also we're looking at check out the overall length. So this one is like checking out the distribution of the thickness. This one is checking out the overall length. So most of them are about like 80 centimeters to like 120 centimeters thick, but there are 120 centimeters long. But there are quite a few that are very short. That may be like an anomaly in the data because some image processing problem. And if we're talking about the image processing tomorrow, you will see there are a lot of glitches that gonna generate anomaly data. So that it's crucial that you check the distribution and get rid of all those like obvious errors. And after we get rid of the errors, we check our data sets. There are like 1,233 pieces in here that are, let's say, with no obvious fault. And the second part is, remember when we mentioned that we want them to do the like this kind of sliding window data augmentations, and in most of the neural network, it requires like the input and output to be fixed length. I don't really have something here. Wait, let me stop. Sorry, I'm sharing. I'm flipping through the computers. Hi, so I'm sharing my other computer. So normally, if you look at all the neural network models, it's something look like this, and there are some like crossovers. Yeah. Yeah, it's something like this. So normally it would require like a fixed number of inputs. So for example, there are, let's say, n is a fixed number. So this one can be 80, like 20, 30, 40, 80, 90, 100. But this one normally cannot be a variable. So if we're like putting at like each value, for example, the thickness. So thickness 1, thickness 2 to thickness n. But remember, we're having strips, like some are longer, some are shorter. So some may only have like thickness 1 to thickness 40. Or no, I think just by checking this one, by checking the distribution, some have like thickness 1 to thickness 80. Someone has thickness 1 to thickness 120, just because the strip is longer. So in this case, we would do a sliding window of, in this case, we did a sliding window of 80. So basically, we only keep the 80 in a length in a certain data set. If it's longer, for example, like 120, we'll just do a like sliding window and get like different segments that each are like 80 long. So they're like all 80 long. So basically each data set has like thickness 1 to thickness 80. And it raises another question. What if we want to train a neural network of changing length? So that's possible. That's another technique called padding. So for example, because in this case, we use the sliding window as the augmentation tool to generate more data sets. But let's say we want to generate a neural network that can handle both input of 80 centimeters long and 120 centimeters long. How do we do it? We use a method called zero padding. So we take the longest length. So from thickness 1 to thickness 80, 81 to thickness 20, 120. And for the shorter ones, eraser. For example, for these ones, we would like what they called, zero pad them, just give them all zeros until it reach like 120 numbers. So they're all 120 long. It's just when you're like having a moment where it's only like the piece is shorter, we would just give it a lot of zeros to make their all even length. So I'm sharing my screen, right? Sorry, I'm paranoid. So this is,
we can see it.
Yep, perfect. So this is like one crucial idea of like, I mean, there are some more complicated ways to handle this, but this is like a most generic and commonly used way, like zero padding, to get all your input data at with the same dimension at the same length. Yep. But in our case, we just crop it to the shortest length and did a sliding window as a method of data augmentation to generate more data. Yep. not sharing this computer. So this is like a process of just clipping everything to 80 points long, and then this one is called normalization. Sorry, I'm having a little bit of Chinese here. So this is called the normalization. You don't really need to understand the code, but I'm just gonna talk about some of the main concepts in machine learning to improve your accuracy. So in case you're doing your own machine learning project in the future and you're having low accuracy rates and low sensitivities, you sort of know where to look for. So the normalization is something like this. So what is normalize? So if you're using Grasshopper, you would know the word normalize is that, for example, if you're a vector that are like 100 meters long, normalize means just put it back to from like 1 unit long. It is the same with machine learning. So for example, if you're having like 0 and x, that's y, and all your data distribution is like this. So, oops. So normalize would be, first of all, putting everything around. So it's like the same data, but you just move everything back to the 0, 0 point. And the second one is to so did you notice, like, for example, this data, like the dimensions, this dimension is extremely long, while this dimension is extremely short. So if the data distribution is like this, imagine you're training a neural network. It may be more sensitive to the variation in this direction, but less sensitive to the variation in this direction, because this one is just not that differentiable. So another goal of the normalization is to get to add a bit scale factor to x and y and have something distribute like more evenly in the space. So basically it's from this one to this one to this one. So first of all, you move to the 0 point, and then you shrink and you scale along different axes to make your entire data sets that fits into the domain of like 1 and 0, 1, or 0, 1 and 1. So for example, like this one, it may fit into something like 2105. I'm just making up numbers, 641. And this one may, oops. Sorry, I'm cleaning things. Or like this one maybe at some place at like 1095.65. So this one may be like your original coordinates, and then you scale everything with a fixed parameter into a fixed into a domain of 1 and like 1 and 0 on our axis. And remember, this data is something that let's say that are not two-dimensional. This one can be like in this case, it's 80-dimensional data. So this is called like a normalize, just shrink down with a certain transform vectors. Okay. So we're back here. And there are some ways to calculate the gradients that we're not going too much. And so after this phase of data augmentation of cutting down a lot of like 80 segment pieces, you see that our training set, our data set suddenly expand from like 1,239 and to this one to 22,427. So our data set sort of just explode. And in the end, we have over 22,000 training data. And if we look at here, we also leave 10 pieces. So we want to leave 10 pieces of synthetic rubber, leave them away for testing to evaluate how accurate our system is. Because we don't want to give a neural network some piece that they have already seen before. We want to give them new piece and to see how they're performing on those new pieces. So those were like, we left 10 pieces for testing purposes. And now you can see what are the data for this one in the first one of X. X is input, so basically it's a gradient. So so those are like the angles at each point, and those are the like thickness on the two end. And if you look at Y, you can see what is in the Y. Oops. I forgot to run this one. Yeah. So those are in the Y. X, I think X is the thickness, Y is the gradient. And here is something I want everyone to play a little bit tonight. So this is the most simplified version of the model. It only have 2 different layers. It's a sequence model. It has like 2 different layers. So one is called dense layer, and the second one, it's not necessarily layer, but it's like a dropout. Those are the 2 most basic level of neural network. And there are a lot of things we can play with it to get ideas of how things happens and what's the like what we call the witchcraft process of the neural net happens. Oops. So what is the dense layer? The dense layer is very simple. For those who still have your Jupyter notebook open, so there is a line called model add dense. Output thing. Sometimes, so this one can be like a variety of numbers. So this one can be 5, 1, 2. Normally it's exponential of 2, so it's like 16, like 64, 128. So normally this number will be an exponent of the 2. And we have a activation. Called ReLU. Normally it's ReLU. Sometimes you can use others. You have outlined this line, right? In your Jupyter notebook. Yep. So First of all, don't touch the first line, the length x0. So basically, first one is that we start with like the length of x0. So how many numbers in x0? In this case, I think it's like 80 numbers or 82 numbers. So 80 gradients plus the 2 thickness. And so the input is 80. So in the first one, in the first model add, the output is 16, right? So basically it will have 82 here and 16 here. And basically it will just link everything. The reason why it's called dense, it's like a full connection model. So that's a most basic part of a neural network model. Basic has no optimization. You just connect every neuron with everything. So this is 82, 16. And if you comment out another line. So for example, if you say we comment out the next line, the next, so ignore the dropout line. So we comment out to the next dense line. It says output dim is 512. So the next layer is having like 512 neurons. And just sort of, you can imagine like everything is connected to everything. And the last line that outputs the length y0. So they will measure whatever is in the length y0. And they will compare to our output of y0. So this is like, so this is y0. So this is our x0. And the trick is that by copying this line of code, you can have as many layers of dense neural network as you want. Like basically the structure is all the same. Like you have certain amount of neurons and they're like just fully connect with each other. So Keras is like very easy to just building up the neural block. So all of this, what they call the like hidden neurons, are something you can play with. You can add unlimited layer. Each layer can have like unlimited number of neurons. So so here, for example, you want to put we can change this one, like the first layer, hidden layer, we're having 16 neurons. So you can change to like 64 neurons, and this one is like 520 neurons, and you can change it to 16 neurons, and you can just add another layer of, let's say 8 neurons, or let's say like 32 neurons. And so this will create different neural network structure just by changing those lines here. And if you keep running, remember like in the earlier conversation, we mentioned about iterations. Here you will just run this line, it will start training. And the loss the loss is the mean square, like not mean square average. Yeah. Mean square error. So this one, the value loss is about the accuracy of your model. The lower, the better. If the value loss is 0, it means it's 100% accurate. So you can see through the iterations, the value loss means like the error start to decrease. And that is your performance of your model. And currently we only use like 20 epoch, like 20 iterations. Normally as the iteration increase, it will be more and more accurate. But I would just encourage everyone to play with these parameters a little bit to get a sense like how many parameters are there, like how the layers would relate to the accuracy. If you increase the layers would be better, or increase the neurons in each layers would be better. So those are like after 20 epoch. So this is like the loss curve. So the training set, test set. And actually this one is pretty good. And if you keep just run it like all down to the bottom, so the red curve is our ground truth. Yep. I think it's reverse, sorry. So the red curve is actually our prediction, and the green one is the ground truth. Yeah, green one is the ground truth. So I got this one reversed. So you could see this one, this model performs very well. And I would encourage everyone just to play with this value a little bit tonight and see what happens. And tomorrow we'll come together to discuss if we can, anyone can get like the lowest error. For example, I'll show you like a horrible model. So for example, let's see. DIM 206, I don't know if it's gonna be horrible, but let me see. Like we said, it's a lot of them are just magic. You never know what you're gonna get. For example, I'm having a few layers of lots of lots. Oh, the one thing. For example, let's say an untrained model, we just let it like iterate one time. The loss would be big. So this is still okay. One moment. Because this is like a very simple connection, like very simple relationship. So we like one simple model normally would do. So if we didn't train the model, this is the output of like a random generated neural network. So it's like the worst you can get. But if we just change the epoch to the normally I think 20 is enough. Just play with these numbers. It doesn't really matter. Like a lot of them are just witchcraft, and sometimes you will have like a significant positive feedback. So remember, this is like the worst it can be. So this way I'm using a very, very, not very, very, but it's quite big neural net. Each layer have like 500 neurons. All right, my kid is here. So I don't know if everyone has started play with it, because like this one, I'm having like many neurons. So the training process is likely to be a lot slower than the previous ones.
When we run the training, is the training through the TensorFlow platform instead using our GPU?
It's not using your GPU. It's just based on normal CPU. So because our data structure is very simple, so it's currently it's not necessary to use GPU. But if we're using like training for image recognition, it's likely that we really need to use GPU. But currently it's just a normal CPU, no optimization. But it is using TensorFlow in the backend. So Keras is just basically a package for the TensorFlow that they package it better, that you can just having this kind of like no-brainer laying out of the neural network structure.
Thank you.
Yeah. So normally when each time when you run, and if you look at here, in the model folder. So in each iteration you run, they will like this one is saved. So it's neural network. So it's just general neural network, no CNN, no STM, and the decimal number behind it is the accuracy of the model. So you can see some of them are more accurate. So the best we are getting here is 0.12. And if you click it open, you can see what are the parameters you're using. For example, this one, the first layer is 512 neurons, and the second layer is 80 neurons. So this model currently, like the score is 0.012345, which is the most accurate models that I have achieved so far. So I would just encourage everyone to play around with these numbers a little bit. And tomorrow we would come together to see who has achieved like the best model.
Where did you find the models that you formerly talking about in the folder? Are you talking about the folder in our drive?
Yes, it's just in your folder, that you have downloaded and from the GitHub. And it's in so if you open the folder from the GitHub, it should look like this.
We're not able to see the folder on your screen.
Oh, sorry. I forgot to share my screen again.
I think it's shared the Jupyter browser, but it's not sharing the.
Okay, so if you open, so this is the folder that you're looking at, ideally. If you get everything from the GitHub, so there's a folder called the model. So ignore those ones. Those are my old ones. So here, like just the txt, if you click it open, you can see like the model structure. So this one performance is not very good, but it has like a lot of neurons and etc.
And maybe it's just me. I think I ran the Jupyter code, the model code, but there is no folder created in here in my browser.
Oh, maybe you can create like an empty model folder. And it will be saved in the model folder. Just create like you can manually create like a empty model folder.
So does this mean I have to run the model code training mode again, and then it will save the epoch results in there?
Just find this line. So this line is just right under the fitting of the gradient descent. So find this line. So this is the saving line. So in this one, I'll just insert a cell above. It's this. So this piece of code is basically saving your model, give it a score, and save it to your model folder. So basically it saves the model itself. So in case you can't find the parameter, you don't need to retrain it. And also it saves like a model summary, which are like what is condition in each layers. And so just play with different layers, and I'll go through 2 more parameters for you to play with. There are 2 parameters. One is called the dropout, and one is called activation. Activation, I think it's more complicated. I don't think we'll have time to cover it like today, but I will share this one in the group chat so that you can change just so currently this one is a ReLU. You can change it to like 10H or sigmoid. Sigmoid is quite popular to see different like activation functions. I'll explain it a little bit tomorrow, but it's very mathematic relevant. But basically like different activation method will have like slightly different output. Sometimes the one type is extremely sensitive for one type of task. Sometimes they're a bit similar, but so I would say just try sigmoid. If I think I spelled it right, yeah, sigmoid. So if I would say sigmoid, this one is probably too much. 64. Well, this one is really good, 0.098 for some reason. So we're using so I have changed some to sigmoid. I think we can change all to sigmoid if you like. So this is the activation function that I will explain more tomorrow. But I'll encourage everyone just to try different activation a little bit. And if you don't know what their name is, you can just search for Keras activation function. So they will have like a bunch in here. Oops. Like sigmoid, softmax. It's also so be careful. I would recommend to use the ones in my picture because there are something like the softmax. Softmax is for categorical probability. So it's for the 0 and 1 problem. If it's a tree, if it's not a tree, if it's a human, if it's not a human. So for this like 0 and 1 problems. So basically it will only output 0 and 1. So do not use this one. But generally, like softmax is pretty similar. YILU is good. Like YILU is something in this chart here. So just try like different ones from here. And you can open here. So here are all the name of the activation functions they have here. I'll put this graph in the chat box. What's the name? Oh, here. So it's in the group chat. And the last thing I will explain today is about the dropout. So that's so there are millions of hyperparameters that you can play and tweak with in a machine learning process, but those are just 3 most basic elements that we're going to cover. So the dropouts is something like this. So for example, if this is a neural network, and sometimes it will, depending on over rely on one feature. Just imagine like if this is a neural network to recognize a panda bear, hypothetically. And each of the neuron will, let's say on the higher level neurons, will have its own like focus. For example, this one will recognize the color of the ears. This one will recognize the color of eyes. And maybe this one will recognize like body shape. But it's a lot more abstract than this, but just give you some intuitive understanding. And this one may be like body color. And as we all know how panda bear looks, so it's very easy for a neural network to over rely on the color of ear, color and the body color to make decision on if this bear is a panda bear or not, or this animal is a panda bear or not, because at least no animal I can think of would have like a white body and black ear. So if we let it naturally train, the decision will be overly rely on these 2 neurons, because those are like distinct feature of a panda bear. However, if we're showing them another image that it somehow, let's say the panda bear is hiding its head or is covered by a tree that you cannot see its ear, then the neural network in this case cannot recognize the panda bear anymore, because it's overly relying on these 2 neurons to make a decision. Can everyone sort of follow along? So dropout is something that in each iteration, it will randomly kill some neurons. So for example, in these iterations, the ear neuron and the body color neurons will randomly be deactivated. So in this case, if those 2 are deactivated, the decision need to be made based on the other neurons. So this is the dropout is a way for the neural net to avoid, like say, over reliance on a certain decision-making neurons in the process. That's why we're having dropouts here. But and it's a mystical process. Sometimes it works really well. Sometimes it doesn't really impact. So feel free to add the dropouts, tweak around the percentage of dropouts, because currently we're having on like 50%. Sometimes you can try 20%, 10%, 90% and see what are the different outcomes. And I will distribute a template. One moment. Yeah. So as the outcome of this workshop, because this workshop we will play with different models and observe how it works. So for the 3 days of the workshop, so today we will work with neural network. Tomorrow, general like dense neural network. Tomorrow we will work with sequence models such as long short-term memory neural network, and maybe the day after tomorrow, if we had time, we'll work with recursive neural network like CNNs. So each day we'll work with a different type of neural network, and I will encourage so it's like required part of the output that each one generate like 3 of these graphs demonstrating like your best outcome of the day. So like the model score, model structure, model gradient descent loss, and some sample predictions. So this one ideally would be my best model of the day, and one like worst model and one mediocre model to see like a range of possibilities. So I will distribute this template and just some homework to encourage everyone to tweak around with the parameters. And in order for you to get different outcomes, I have already noted here. So get a segment to test. So there are remember we have left 10 segments as the testing set. So here, so I smaller than 10, we have 10 segments as our testing set to see how the system works. So basically in here, you can choose a number between 1 to 10. So I think it starts at 0. So you should be like between 0 and 9. And because each segments are like cut into a lot of like 80 centimeter long cases, so you can change pieces. So you can change this one, like if it's 1, it's like first piece. But because it's uneven length, so some may have 10 pieces, some may have 3 pieces. So if it's out of boundary, you just get like a smaller number for this. So just pick another one and see how it performs on another piece. So just a smaller home exercise for everyone to play around. And another thing you can change is the epoch. It's like the iterations, number of iterations. For example, I'm only training 20 iterations, but for bigger models, sometimes you can train like 200 iterations, because ideally when they increase, it could become like more and more accurate. You can see the accuracy has been improving. The error has been descending. So it's like So it's so today is just 3 of this template for our neural nets, and one of them have to be your best result. Because I'm having another meeting like 10 minutes from now, so are there any questions? We will have a tutorial session tonight, and the Guanqi will be here for any debugging issues. There will not be new contents, and it's optional for you to drop in and off to ask questions and help with like software and etc. So everyone is having this code running. Yep.
Mine doesn't run, but I guess should I just wait for the later meeting and maybe go with that Guangji to go over that? Because mine has like a kernel error. So I don't think I installed it correct.
So normally you can restart your kernel and interrupt or restart here, but if it's still not working, it's problem with installation of TensorFlow or Keras. Maybe Guanqi can help you tonight.
Yeah, I did that. So yeah, I'll maybe just meet later tonight and see if we can get it fixed then. Thank you.
Perfect. So any other issues or any questions about the structure of neural network? Or this is like the easiest neural net. So I think it's a pretty straightforward. So if you want to add a dropout layer, you just cross this one out and you can change the dropout to 0.2 or something. You can change your activation to tanh or sigmoid or renlu or yilu or etc.
So in the activation function that you're showing, so it's fairly common to use different activation functions as a different hidden layers.
Normally it depends, but my personal preference would just keep them uniform, like more or less, except the final layer. So normally there will be different one for the final layer, but for me, most of them interim layer are the similar, but it's like I said, it's like more like a magic. I would encourage you to try a little bit. But personally, I would keep all the other layers the same. And there are, I mean, which one works better really depending on the distribution for the data. And there is like no way to know for sure. A lot of them are experience-based. Normally, ReLU and the sigmoid works best for the majority of cases. And there are something like leaky ReLU if there are some like tricky things happening in ReLU. There's another like ELU or leaky ReLU that are slightly more advanced. But like sometimes, in most of the times, for me, they're indistinguishable, like the leaky ReLU and ReLU, but sometimes it works miracle. Yeah.
Thank you.
Yeah, and also you can add more layers. You can add like 20 layers, 30 layers. If you want just another layers, you can just basically get one and you can just get another one, like a lot of them. And another thing is be aware, like so for the models, if you open there, so you see the total number of parameters. So those are the parameters in the model they need to adjust in each iterations to give you the result. So you can see sometimes they are like a lot, sometimes they're not. But so for example, this one is probably smaller, 9,000, but this one, let's say they go up really quickly. And this parameter, the number of parameters normally relates to your training speed at each epoch. But because our model is very simple, so it won't matter much. But if we're doing some image-based recognition, it can easily go up to like 5 minutes for each iteration. And imagine like you have to train it for like 300 iterations, 500 iterations. The time quickly accumulates. But it's okay. I think it just for the first stage, just get a sense of the number of neurons at each layer, get a sense of the parameter versus training speed versus accuracy, and just feel around the accuracy of the models of the different dropouts of the different, let's say, activation programs. A lot of them are just kind of a sense that you develop when you're playing a lot with different parameters. Yeah. Okay, I need to hop off. And good luck, everyone. See you tomorrow.
Thank you.
Yep. If you're having questions, feel free to post in the group chat.
For the meeting later tonight, is it the same Zoom link?
Yes, I think so.
Okay. Thank you.
Thank you.